Here I will discuss construction of character table using quadratic functions of Cartesian coordinates as basis. I will use the functions x square minus y square, xy, yz, zx, and z square. These are the d-orbital functions. Then x square plus y square, x square plus y square plus z square, and so on, quadratic functions like these. This is an s-orbital function. And I will consider the point group C4V because this is a continuation of my earlier video where I discussed construction of character table of this point group with linear functions of x, y, and z. The symmetry elements and coordinate system are shown by the usual diagram. This is the x-axis, this is the y-axis. The z-axis acts as the fourfold axis of symmetry of the point group. It is perpendicular to the plane of the paper and is indicated by a dark square to indicate that it is a fourfold axis of symmetry. This one, sigma xz plane is sigma v1. Similarly, sigma yz plane is sigma v2. Sigma v2 plane is like this. And the dihedral planes are like this, sigma d1 and sigma d2. Sigma d2. I discussed these in my earlier video, and I will apply the symmetry operators on these functions one by one. First, let us take up the function, say x square minus y square. If we apply C4 operator on x square minus y square, what happens? The result is this. By C4, x turns to y and y turns to minus x. Therefore, this is y square minus x whole square. This is minus x square minus y square. If we apply sigma v1 operator on x square minus y square, the result will be what? Sigma v1 keeps x unchanged and turns y into minus y by reflection. So this is x square minus y square. Sigma d1 on x square minus y square. Sigma d1 turns x into y and y into x. Therefore, this becomes y square minus x square. So this is minus x square minus y square. What about the C2 operator? C2 on x square minus y square will give what? X turns into minus x by a 180 rotation. Minus y turns into minus y. So we get the same function back. In this way, if we go complete the list, we will find that x square minus y square is either kept unchanged or is turned into its own negative. It does not mix with other functions of the basis set, and therefore we get a partition here. So x square minus y square will act as a basis of a one-dimensional irreducible representation of C4V. And what will be the characters of that representation? If we write in this manner, character, then E, and the two C4 operators, because we know that C4 and C4 three times will have the same character. They are conjugate to one another. C2, then 2 sigma V and 2 sigma D operators. And we write basis in this column. What will be the characters? Basis is x square minus y square. And the characters will be, for C4, the character will be minus 1. Because actually this is a matrix minus 1 multiplied by x square minus y square. And trace of the matrix is minus 1 itself. So trace is minus 1 for C4. For E keeps this unchanged. Therefore the matrix will be 1 within bracket and trace will be 1. C2 keeps it unchanged, gives character 1. Sigma V keeps it unchanged, gives character 1. Sigma D changes the sign, gives character minus 1. So this is the set of characters for a one-dimensionally reducible representation with this function x square minus y square as basis. Let us give it a name, gamma 1. An arbitrary name which will be replaced by American symbol later on. We next try the function yz. What is the result of C4 on yz? What is the result of C4 on yz? Coordinate system is here x, y, z, sigma d1, d2, sigma d1, d2. C4 yz, y turns into minus x and z remains unchanged. Therefore, we get a new function xz from yz. So let us apply the same operator C4 on the new function that we have obtained. What is the result? X turns into y and z remains unchanged. This shows that xz and yz are coupled together, at least under the action of C4. Then examine the action of sigma V1 operator on yz. What happens by sigma V1 is this. Sigma V1 is this plane. Y turns into minus y, z remains unchanged. We get minus yz. And sigma V1 on xz, because we are considering two functions at a time, so x becomes on reflection on the xz plane, x remains unchanged and z also remains unchanged. We get yz xz. What about sigma d? Sigma d1 on yz will give what? Sigma d1, this is sigma d1, x turns to y and y turns to x. Therefore yz will give xz, and sigma d1, the same operator on xz, will give yz. We thus see that in the basis set yz, zx, these two functions are operating together. They are coupled together under the action of all these symmetry operators. So we get a partition like this. They will not mix with the other functions of the basis set. So we expect a two-dimensional irreducible representation with these two functions and basis as basis. And therefore we have to write these results as linear combinations of these two functions. This function, this result minus xz should be written as 0 into yz minus 1 into xz. And this should be written as 1 into yz plus 0 into xz. In this case, we have to write, here we have taken yz first, xz next. This order is to be maintained throughout, yz first, xz next. If you may take xz first, yz next, then that order should be maintained throughout. One particular order should be maintained throughout. We are taking yz first, xz next. Then minus yz should be written as minus 1 into yz plus 0 into xz. This should be written as 0 into yz plus 1 into xz. This is required for expressing the results in matrix form. This should be written as 0 into yz plus 1 into xz, and this one as 1 into yz plus 0 into xz. In this way you can go on. From these two lines we get a matrix form. We get a matrix form for C4 operator. What is that? You have to take these coefficients row-wise, 0, minus 1. 0, minus 1 in the first row and 1, 0 in the 1, 0 in the second row. These results can be expressed, these two results actually can be expressed as this. 0, minus 1, 1, 0 matrix multiplied by the row by the column matrix yz zx will give 0 into yz minus 1 will give minus zx. Minus zx, here we have got it. 1 into yz plus 0 into xz will give yz. Yz, we have got it here, yz. So this matrix multiplication is coming from here, and therefore this is the matrix representation of C4 operator. And what is the trace of the matrix? Matrix is 0. In this way we can construct all the matrices and calculate all the traces for all the operators of C4V, and the characters will be written in a tabular form like this. Identity, then 2C4. You will find by doing works like this that C4 cube also will give you the same trace of the matrix. C4 gives 0 trace. C4 cubed will also give a trace 0. Then C2 operator, then the 2 sigma V operators, and then the 2 sigma D operators and basis. Under basis you have to write two functions, yz, zx. They are acting together. This is indicated by this bracket. And the irreducible representation is of dimension 2, because the matrices are of size 2 by 2. It is irreducible because you cannot reduce the size of the matrix further, because you cannot separate these two functions from one another by any of the symmetry operators of C4V. That is why the representation is irreducible. And what is the character of E? In a two-dimensional representation, identity is represented by a unit matrix like this, 1, 0, 0, 1. This is the matrix representation for the identity operator. So character of identity will be 2. C4 has got character 0. C2, what about C2? Have we calculated it? C2 will give a character of -2 because YZ turns into minus YZ. By C2 rotation, Y turns into minus Y, X turns into minus X, and therefore by calculating the matrix, you will find that the trace will be -2, and these two will have character 0. This is another irreducible representation coming from these two functions as basis. Let us give it a name, gamma 2. In this way, using the function xy, you will get another irreducible representation, different from the two that you have obtained so far. xy will give you another irreducible representation, gamma 3. I am not going to do it. You may do it by following this procedure, and you may check your results against character tables given in standard textbooks. I am not doing it here. Similarly, by using the function z square, what will happen? Z does not change under the action of any symmetry operator of the point group, and therefore z square will remain unchanged, and characters therefore will be 1, 1, 1, 1, 1. This is another representation, call it gamma 4. We have obtained gamma 1, and here gamma 2, gamma 3, and gamma 4. You may recall that this same representation was obtained with x, y together as basis when we considered linear functions in an earlier video. Similarly, we got this irreducible representation with z as basis. Here I am not using a bracket because z square can separately act as a basis, z can separately act as a basis, but here x and y together will act as a basis. These two functions together will act as a basis set. Therefore, brackets are needed here for multidimensional representations. If you consider the s-orbital function, x square plus y square plus z square, that will also remain unchanged under the action of symmetry operators. That will also give this totally symmetric irreducible representation. So these are 4 possible representations that we have obtained, but this is not an exhaustive list of irreducible representations for C4V. There may be other irreducible representations, and I will try to find out those using other types of functions or vectors involving Cartesian coordinates. That will be dealt with in a next video.